In this video, I'm going to show another worked example of drawing correct resonance structures. Now, the first step is to identify the lone pairs of electrons. So, for the carbonyl oxygens, there's going to be two lone pairs to make up the octet of 8 electrons because there's already 4 electrons in each double bond and therefore 2 lone pairs are needed. And there's no charge on those oxygens because there's 6 electrons around the oxygen, so it's neutral. Now the negative charge is actually shown in this structure, and these types of compounds are dicarbonyl compounds because there's 2 carbonyl bonds. But what's special about them is the protons that are present on that carbon that's in the center of the 2 carbonyls. If I just draw it out again here very quickly, these 2 hydrogens are actually quite acidic, and the reason being is that when one of those hydrogens is removed by a base, so we take away one of those hydrogens and we're left with a carbanion, which is exactly what's shown here, this negative charge can be stabilized through resonance. So that's what we're going to have a look at. How can this negative charge, these 2 electrons, be stabilized by resonance? So there is actually 2 electrons present there, which is why there's a negative charge. And what isn't shown, if I just draw it in blue, because we don't normally include that hydrogen in these skeletal format of molecules, the way we draw them, there is that one hydrogen that's from here is still present on the molecule. Okay, the next step in drawing resonance structures is to identify the conjugation path. We're going to be starting at the negative charge because that's where the electrons are going to move from. And we have from the negative charge a single bond and a double bond going in that direction. But we've also got a second conjugation path, identical single double bond moving towards the other carbonyl oxygen. So that's the path length along which these electrons can be delocalized to stabilize this carbanion. Okay, let's now move and have a look at how to draw a resonance structure by moving the electrons into the adjacent single bond. So the first thing I'm just going to do is include all of the lone pairs of electrons, and now I'm going to use a curly arrow to show the movement of 2 electrons into that adjacent single bond, and then from the double bond the electrons are pushed up onto that electronegative oxygen atom. Looking at the resulting resonance structure using the resonance arrow, I will draw out the bonds with single bonds first, include my oxygen atoms. This carbonyl, the electrons have not moved, but I have a new double bond here between the 2 carbons. There's now a single bond to the oxygen and there's a negative charge on the oxygen. So if I just finish it off by ensuring that I've got all of the lone pairs of electrons, notice that I started with a negatively charged molecule, and my resonance structure is also negatively charged, so charge has been conserved. So now I'm going to draw the resonance structure, this time moving the electrons towards the left hand side. So I show my curly arrow moving into that single bond from the double bond onto the oxygen atom. And again we draw out the resulting resonance contributor. I'll draw all the atoms first and all the single bonds, and then I'll have a look to identify where I have any new double bonds. So this carbonyl bond, the electrons haven't moved. I have a new carbon-carbon double bond here, and I have a negative charge on my second oxygen atom where the electrons have moved to. And I'll just include the lone pairs there to ensure that I've accounted for everything. So notice again we have a negative charge, so charge has been conserved. When I was drawing this second resonance structure, I started again from the original starting molecule. And I just want to show you something. If we go up here and look at the very first resonance structure that we drew, I can actually move the electrons into the single bond, from the double bond across into that single bond, from the double bond onto the oxygen atom, because our conjugation path is right the way from one oxygen across the single double to the other oxygen. And when you draw out the resonance structure from those curly arrows, you end up with the second resonance structure that we drew here. So if you want to, you can always draw resonance structures from moving electrons from the previous resonance structure that you've drawn, or you can equally arrive at the same resonance structure by going back to the original starting molecule. Both are right. It's just to show you that you will get the same correct structures either way. I hope you found this video really useful, and see you all very soon.